Sorry for starting the presentation with a cough. I think I still have a little bit of a bug going around. But now I want to continue with the 45, 45, 90 triangles. So in the last presentation, we learned that either side of a 45, 45, 90 triangle that isn't the hypotenuse is equal to the square root of 2 over 2 times the hypotenuse. Let's do a couple of more problems. So if I were to tell you that the hypotenuse of this triangle, and it's a 45, once again, this only works for 45, 45, 90 triangles. And if I just draw one 45, you know the other angle's got to be 45 as well. If I told you that the hypotenuse here is, let me say 10, right? And we know this is the hypotenuse because it's opposite the right angle. And then I would ask you what this side is, x. Well, we know that x is equal to square root of 2 over 2 times the hypotenuse. So that's square root of 2 over 2 times 10. Or x is equal to 10, is equal to 5 square roots of 2, right? 10 divided by 2. So x is equal to 5 square roots of 2. And we know that this side and this side are equal, right? I guess we know it's an isosceles triangle because these two angles are the same. So we also know that this side is 5 over root 2. And if you're not sure, try it out. Let's try the Pythagorean theorem. We know from the Pythagorean theorem that 5 root 2 squared plus 5 root 2 squared is equal to the hypotenuse squared, where the hypotenuse is 10. It's equal to 100. Well, this is just 25 times 2, so that's 50. Plus 25 times 2 is 50. This is 100 up here. Is equal to 100. And we know, of course, that this is true. So it worked. We proved it using the Pythagorean theorem, and that's how actually we came up with this formula in the first place. Maybe you want to go back to one of those presentations if you forget how we came up with this. I'm actually now going to introduce another type of triangle, and I'm going to do it the same way by just posing a problem to you and then using the Pythagorean theorem to figure it out. This is another type of triangle called a 30, 60, 90 triangle. 30, 60, 90 triangle. And if I don't have time for this, I will do another presentation. Let's say I have a right triangle. That's not a pretty one, but we'll use what we have. That's a right angle. And if I were to tell you that this is a 30-degree angle, well, we know that the angles in a triangle have to add up to 180. So if this is 30, this is 90, and let's say that this is x. X plus 30 plus 90 is equal to 180, because the angles in a triangle add up to 180. We know that x is equal to 60, right? So this angle is 60. And this is why it's called a 30, 60, 90 triangle, because that's the names of the three angles in the triangle. And if I were to tell you that the hypotenuse is, let's say the hypotenuse of this triangle, instead of calling it C like we always do, let's call it H. And I want to figure out the other sides. How do we do that? Well, we can do that using pretty much the Pythagorean theorem. And here I'm going to do a little trick. Let's draw another copy of this triangle, but draw it exactly, flip it over, draw it the other side. And this is the same triangle, it's just facing the other direction, right? If this is 90 degrees, we know that these two angles are supplementary. You might want to review the angles module if you forget that two angles that share kind of this common line would add up to 180 degrees. So if this is 90, this will also be 90. And you could eyeball it, it makes sense. And since we flipped it, this triangle is the exact same triangle as this. It's just flipped over to the other side. We also know that this angle is 30 degrees. And we also know that this angle is 60 degrees, right? Well, if this angle is 30 degrees and this angle is 30 degrees, we also know that this larger angle goes all the way from here to here is 60 degrees, right? Well, if this angle is 60 degrees, this top angle is 60 degrees, and this angle on the right is 60 degrees, then we know from the theorem that we learned when we did 45, 45, 90 triangles that if these two angles are the same, then the sides that they don't share have to be the same as well. So what are the sides they don't share? Well, it's this side and this side. So if this side is h, then this side is h, right? But this angle is also 60 degrees. So if we look at this 60 degrees and this 60 degrees, we know that the sides that they don't share are also equal. Well, they share this side. So the sides that they don't share are this side and this side. So if this side is h, we also know that this side is h. Right? So it turns out that if you have 60 degrees, 60 degrees, and 60 degrees, that all the sides have the same length, or it's an equilateral triangle. And that's something to keep in mind. And that makes sense, too, because an equilateral triangle is symmetric no matter how you look at it. So it makes sense that all of the angles would be the same, and all of the sides would have the same length. But, when we originally did this problem, we only used half of this equilateral triangle. So we know this whole side right here is of length h. But if that whole side is of length h, well then, this side right here, just the base of our original triangle, and I'm trying to be messy on purpose. Let me try another color. This is going to be half of that side, right? Because that's h over 2. And then this is also h over 2, right over here. H over 2. So if we go back to our original triangle, and we say that this is 30 degrees, and that this is the hypotenuse, because it's opposite the right angle, we know that the side opposite the 30 degree side is half of the hypotenuse. And just a reminder, how did we do that? Well, we doubled the triangle, turned it into an equilateral triangle, figured out this whole side has to be the same as the hypotenuse, and this is half of that whole side. So it's half of the hypotenuse. So let's remember that. The side opposite the 30 degree side is half of the hypotenuse. Let me redraw that on another page, because I think this is getting messy. So going back to what I had originally. This is a right angle. This is the hypotenuse, this side right here. If this is 30 degrees, we just derived that the side opposite the 30 degrees, the side opposite, right? It's like what the angle is opening into, that this is equal to 1/2 the hypotenuse. If this is equal to 1/2 the hypotenuse, then what is this side equal to? Well, here we can use the Pythagorean theorem again. We know that this side squared plus this side squared, let's call this side a, is equal to h squared. So we have 1/2 h squared plus a squared is equal to h squared. This is equal to h squared over 4 plus a squared is equal to h squared. Well, we subtract h squared from both sides. We get a squared is equal to h squared minus h squared over 4. So this equals h squared times 1 minus 1/4. This is equal to 3/4 h squared. Excuse the cough. And once again, that's equal to a squared. I'm running out of space, so I'm going to go all the way over here. So we take the square root of both sides, and we get a is equal to, the square root of 3/4 is the same thing as the square root of 3 over 2, and then the square root of h squared is just h. And this a, remember, this is an area. This is what we decided the length of the side. I probably shouldn't have used a. But this is equal to the square root of 3 over 2 times h. So we've derived what all the sides relative to the hypotenuse are of a 30, 60, 90 triangle. So this is a 60 degree side. So if we know the hypotenuse, and we know this is a 30, 60, 90 triangle, we know the side opposite the 30 degree side is 1/2 the hypotenuse. And we know the side opposite the 60 degree side is a square root of 3 over 2 times the hypotenuse. In the next module, I'll show you how using this information, which you may or may not want to memorize, it's probably good to memorize and practice with because it'll make you very fast on standardized tests, how we can use this information to solve the sides of a 30, 60, 90 triangle very quickly. See you in the next presentation.